Okay, so welcome everyone to this session. I think we have some exercise sheets to talk about. Also, Whitbag is up and running, so if you have questions, let me know. Apart from that, we have, I think, a lot to talk about: Solidity, smart contract development. Doing some coding together on Remix, taking a look at some wallets, taking a look at how to call functions, how to look at them at Etherscan and see what the impact is there. And we also have a first question on Tweetbig. I think we can do this before we start with everything else and then continue with the sheets. So the first question today is, or one of the questions, how is gas handled in the case of an asynchronous oracle? Wouldn't the owner of the oracle have to pay for the gas which is required for executing the callback? So we're talking about here about design patterns in Ethereum, and in design patterns we have something like an oracle, and an oracle gives us data from the real world on-chain, because we cannot access data from the on-chain from external sources because of the determinism of our Ethereum virtual machine. And now we have a oracle which is a synchronous oracle and a asynchronous oracle, and maybe we can take a look at the slides here and then get a bit of an understanding of what's going on here. So we have, let's do it like this. Let's switch here to PowerPoint. Let's do it like this. And we have a oracle pattern here. And we have two ways of doing this, so the synchronous oracle and the asynchronous oracle. And first of all, the synchronous oracle basically has a repeating oracle service which writes data to the oracle contract. So if you want to get data, you just call the oracle contract and it returns data to you the second you ask. So it's synchronous, but the data needs to be updated periodically. So that's sometimes expensive. And in the asynchronous oracle, you just let the oracle contract and therefore the oracle service know that you are in need for data, and the oracle service listens to the event emitted by the oracle contract, emitted by your transaction, in terms of, okay, hey, I need data. And the oracle service then responds onto that and writes the data to the oracle contract, and the oracle contract calls the smart contract here. And the question is, how is the gas situation handled here? And in terms of oracle service, first of all, needs to get paid gas for writing data and then for sending the data to the callback function of the smart contract. So how can you handle data there? And that's a valid question here. Or how can you handle the costs here? And it's also the same here, because also here the oracle service has to write data to the oracle smart contract and has to pay for that. So actually there is not too much difference here in terms of costs. And what these oracles usually have, either they are owned by the parties who need the data themselves, so they don't have to pay themselves because they pay all the costs. Or if this oracle service or this oracle contract is operated by an independent third party, then obviously you need a way to pay for that. So usually these oracle contracts are paid with a small fee to cover the costs and to cover the cost of operation that's going on in the system here. So that's very important. That's very that's what's going on there. I don't have an example here right now, but if you look up oracles, that's something that's very common here. Okay, I think we can start with our exercise sheet. Yesterday we talked a little bit about one word to the lecture yesterday. We did not quite finish with that. Unfortunately, and we will have to take this with us into the next week. Nonetheless, we will talk about the exercise sheet today and take a look at that. And maybe it could be the case that we will run out of time for the Ethereum slide, so that we take longer than the 4 weeks we have. And then we will cover the last parts of the lecture within the exercise, so that we don't miss anything. But also noted that we uploaded a solution, or not a solution, we uploaded a exercise sheet for the last Ethereum session on GitHub from last year, so it's there, but this is only an optional exercise. So this is nothing we did last year in the lecture or in the exercise, but it's more an optional way if you want to dig deeper into it, but it's not required. So it could be the case that we leave this one out and instead finish the contents of the lecture there. But I'll keep you posted about that. Okay, so let's talk a little bit about the exercise sheet. I'll move it here. So here it is. So exercise sheet 7 from last week, starting with the first question. What is the difference between an abstract contract, an interface, and a library in Solidity? So these 3 are concepts that we are introduced in the lecture, and I try to briefly summarize them to my understanding, so that you get a better understanding of what they are and how you can use them. So first of all, an abstract contract is a contract which has not all functions implemented. So you can define functions in terms of, okay, what is the name, what are the parameters, and what are the return values, but you do not have to implement them. So it could be the case that some functions of this contract are implemented and other ones are not, making this an abstract contract. An interface, so an interface is, in the difference to an abstract contract, is it cannot implement a single function. So all functions only have to be defined in terms of name, parameters, and return values. But apart from that, no function can be implemented. And these 2 concepts, so abstract contract and interface, they cannot be deployed on a blockchain or as a smart contract, because they cannot compile. So you cannot compile these 2 versions. So if you have a smart contract which implements either the abstract contract or the interface, they need to implement the missing functions. So the functions which are not implemented yet need to be implemented if you import abstract contract or an interface. And the library is something that is a full smart contract, so to say, but usually libraries are only implemented once, or only deployed once on the blockchain. And with that, we rely on them from other smart contracts by using a delegate call function. So you can take the delegate call and call the function from this library in the context of your smart contract. So for example, that works very well, for example, with the SafeMath. So there's a lot of contracts out there which rely on a single smart contract, a SafeMath library smart contract. So that's the important part here. And so these are the 3 concepts and how they can be used. Okay, let's continue to the second question here. Are these statements true or false? Give a short explanation. Every pure function is a few function. So let's recall again, a pure function and a few function are, we can define them by stating a pure or a few keyword within the function header. So if we, for example, go here to say, does it work? Yes. So you have some kind of a function test. Then you have a keyword public, that's or private or internal, but you can also define something like pure or few here. And these would allow you to basically define a function as, in case of few, as only reading. So you're not writing to the state. And you can define a pure, and it's not even reading. So it is only relevant to itself. So all the data that it needs is provided within this function. So if you think about that, then it's for example, if you have a function called multiply or add or something like that, and you provide both the numbers, then you do not really access anything on state, on chain, and therefore you're really not reading any of that state. And in the solution, we did it like this. So view only reads the state and does not modify the state. And pure neither does modify and does not read. So you could say that pure is a subset of the few functions here. So that is the solution to this question here. So every pure function is a few function because it's a subset of each other. The second question is: a transaction that calls a few function does not cost any gas because it does not change state. And I think that's a very interesting question. That's also something I think I mentioned yesterday, or not yesterday, last week, when we talked about the topic. And maybe we can do a simple example here so that you get an idea how that works. So we go to our Chrome here, take it like this so that you see a little bit what's going on here. Maybe we can zoom a bit bigger. Very good. Take a new file. Let's do something like 0.5.1. Contract test. Then we need something like a constructor. It's public. We do not really need something in here. What we need is some kind of uint 256 public number. And then we say function view number. We don't need an argument here. We say public, we say few, and we say we need a return statement here because we want to return something here. So returns uint 256, and then we say we return number. So that's a valid smart contract. And we can see here, we got a lot of smart contracts already deployed here for later on, but now we can take this test and say we want to deploy that. And we see we wouldn't have to do this. The number is 0. And maybe we wanna, and that's a few function, so it does not cost any gas right now because my guest client or my client here in the browser just executes it in the second locally. Why? We only read from the state, we do not modify the state. So therefore it's free of charge, so to say. But now we could write something like a function called increment and say we increment public, and it's not few and it does not return anything. But what this function does is basically it says, okay, number is few number plus 1. So that's obviously, I need to put some brackets here. And now I can remove the smart contract here again. I can deploy this smart contract. Let me just remove this one, then you don't get too confused here. So what we have here is right now we have this few number, so it's 0, and we can create an increment transaction. That's just what's going on here. So 20,900 execution costs, so 42,000 transaction cost. And if you click the few number here, it was incremented to 1. And I cannot really show this to you because I don't, I'm not too sure how to debug it correctly. But what you see here is that this this execution of this few function becomes part of this write function, and therefore we need to pay gas for this few function because everyone has to be able to or everyone needs to check if the results from this transactions are correct or the execution is correct, and only then we can really make sure that the chain state is consistent. So in this case, the few function is free, but the few function, if it's getting a part of a transaction, then it becomes costly. No questions here from Tweetback. How much weight do you get if someone uses your deployed smart contract? It really depends on what comments are executed. So usually people, you do not, so what you mean with weight, I think, is something like a transaction cost. Or and this is not something you get, but the miner get. So if you mine a block and it contains a smart contract execution, then you as a miner receive the fee, so to say. And if you want to earn money with your smart contract, then you need to do something like that. You need to say, okay, we want to do it payable. So this smart contract, this function accepts monetary funds. And then you can do something like require and say, okay, MSG point value needs to be larger than 1 Ether. And only if that's the case, so I'm not too sure if that sounds wrong here. That looks good. And then only if I put in 1 Ether, then this increment can work. So that's something that that's going on here. What's the difference between execution cost and transaction cost? Transaction cost is the overall packet in terms of minimum transaction fee in terms of 21,000 gas, plus what is required for the storage of your input values. So you have some kind of input data and the execution that is done with the input data. So for example, the input data is the information that that's the information that what function you want to execute or what arguments you provide to this function, and the execution cost is cost itself. So what is the amount of work that has to be done for executing all this information you provided within the smart contract. So that's the difference here. And the execution cost only is what the smart contract calculation does, and the transaction cost is usually only that in terms of what data. And the transaction cost is the overall package, so to say, plus the 21,000 gas. Very good. Okay. Then let's continue here. Take a look, and so we understood this one. See, in Ethereum, a smart contract that has no functions that are declared payable cannot receive any ether. So if you look here, and if you look back to my Chrome window, and we have this function, let's do like this. So I'm just deleting these smart contracts, or I'm removing these smart contracts here and redeploying new ones, so don't get confused. It's not the same command contract, it's always a new one. So we create a new one, and now we say, okay, we want to increment, maybe we just want to send, we want to send money to the contract, something like that, 1 ether. The contract does not let me do that. So the software says, okay, in order to receive ether transfer, the contract should have either receive or payable fallback function. So the fallback, so directly transferring doesn't work, and this one doesn't work as well. So I'm not able to execute, I'm not able to send ether to the smart contract. That's the case here. So usually if there are no functions which are declared payable, then you cannot send money to the smart contract. But there are two small, how would you call it? There are 2 ways to actually do it, but very highly unconventional ways. And that's, but that's is something you have to keep track of, or you know about, because some hacks have occurred where people really misused this to gain an advantage. And there are 2 ways to do that, and the first one seems stupid, and I think not everyone can do this, but a miner can take his Coinbase transaction, the money from his transaction fees plus mining reward, and put the smart contract as a receiver of this Coinbase transaction. And this is something the smart contract cannot prevent to receive money from. That's a way, first of all. The second way is if another smart contract self-destructs and sends in the self-destruct, you can also put in an address and say all funds on my smart contract or on this destructed contract should be transferred to this other smart contract. And with that, you're also able to give the smart contract money. And a third way is not actually sending the smart contract money, but you can send money to the smart contract before the smart contract gets deployed. Why is that the case? Because the address generation for new smart contract addresses is deterministic. So it only depends on the sender address plus the transaction nonce. And this is hashed and used as a new address for the smart contract. And as no nonce is repeated twice and no address is repeated twice, therefore you can send money to smart contracts before they are deployed. And this is something that's dangerous because if you, for example, if you have a balance value which keeps track of your balance of your smart contract, and people can modify that without you knowing, or without this value changing, this can have some unexpected side effects, and that's something you should account for when developing Solidity code. So let's switch back to Oxid here. Okay, so let's take a look here at the next questions. Our Solidity standard int and uint data types can each hold 2 to the power of 32 different values. So that's not correct. They can hold 2 to the power of 256 different values. So this is how it's defined in the white paper, in the yellow paper, and therefore, yeah, that's that's a detail we just wanted to point out, but nothing that what we are we would ask in an exam. If msg.sender equals transaction origin, then this code was called directly by an externally owned account and not by another smart contract. So if you recall, again, that's something we talked about last week in terms of transactions versus messages, then a message can only be created, so to say, by a smart contract, and a transaction can only be created by an externally owned account. So, and if the origin of a transaction equals the sender of this message, then this is in fact an externally owned account and not by another smart contract. So what I said right now was that messages can only be created by smart contracts. So why can we access msg.sender when only a smart contract was called from an externally owned account? And that's I think that's some inaccuracy within the terminology of Solidity, because msg.sender is always the party or always the address that calls the function. So if you say, okay, msg.sender, I want to access that, then you receive the address that really called this function that's invoked. And but the transaction origin can be something else, like in terms of the original smart contract. So let's make an example here so that you get the idea here. So we have this we have an EOA calling a smart contract, calling a smart contract, calling a smart contract. So that can happen. That happens. I think that's unusual, but you could build something like that. But if we now look at this smart contract here, they don't really know. So this is unknown. So this is we don't know what's going on here when we look at this smart contract here. But what we see is we see 2 pointers. That's the MSG sender. That's this smart contract here. And what we see is the transaction origin. And the transaction origin always points to this externally owned account, but this MSG sender always points to the next one. So depending on the state you're executing this. So if MSG sender is executed here, then it points to this smart contract. If MSG sender is executed here, it points to this smart contract, and so on and so on. But if you want to really ensure that you are called by an externally owned account, then you need to make sure that if it's something like that, only in that case really MSG sender is this one, and also transaction origin is also this one. And if they are equal, then you are good, ready and set. So that's the advantage here to use these 2 parameters. And from my point of view, this transaction origin is useful for ensuring that your smart contract is an externally owned account. But apart from that, you cannot really use it. This transaction origin, you cannot really use it for authentication mechanisms, because once you call another smart contract, you basically give them the allowance to call other smart contracts because you execute them. And the developer of this smart contract really controls the flow of what's going on, and could misuse your execution to execute some other smart contracts on behalf of you, which might not be your intention. So there are some other ways to enable something like on behalf transactions on behalf, something like that. But regarding that, That's another story. But never ever use transaction origin for authentication. Very, very important. Very good. Continue. Yeah, so that's about the questions. I see some questions answered by my colleague. Thank you very much. Next question. Throughout this exercise, we develop and deploy a Solidity Hello World program on Ethereum test network. So, what is a test network and why should we use it? So, generally, a test network is a network that is fully functional, fully operational as the main network. And but the difference here is that the monetary value on the system, the Ether, they don't have any value. So they are worth nothing. You get them for free. They are given to you for free because you should test software on it, but you never should run some kind of productive software on it, because they are not expected to function properly or to run properly, and they can break down many times. So that's the important part here. Question B, what are the 3 largest Ethereum test networks and what are the differences? So we have Ropsten, Kovan, and Rinkeby. These are the 3 test networks that are the largest one, and there are also further ones. So if you, and that's the wrong one, if you look here, and for example in my Chrome, you can go to Etherscan. You can look here, and we have also the Görli testnets. Görli is Görlitzer Park in Berlin, because they founded it there. And so there are many more testnets, and anyone can set up. But Etherscan currently supports these 4, and there are differences between them. So, for example, I think Ropsten is also proof of work based, like the mainnet, but has a very low difficulty. Kovan is, I think, run by some institutions which keep track of the network, so they have a proof of authority algorithm. And the Rinkeby network has some other quirks and has a 15 seconds block time in comparison to Kovan, which has a 4-second block time. So these are a little bit the differences, but they do not really are not really important to us. It's good to know that they are different implementations, and they have also other differences in terms of they might support newer opcodes. So, for example, testing new versions of Ethereum are usually tested first on the test networks before they get deployed to the mainnet. So that's also a little bit testing networks for the Ethereum developers. And for our part, so I do like Ropsten. It's very easy to get gas there or Ether there for free. So that's really what's very useful. Okay, let's go to C. Create an Ethereum wallet and get some Ether on the Ropsten network from a faucet. Note, you do not need to pay anything for this. Getting Ether on a test network is completely free. So I think we already did this. When you go to when you Google Ropsten faucet, you are here, and then you can copy your address. Oh, you don't see that. Let's make it like this, because I think you can go here, copy your address, enter your data, and you receive the money on Ether to my account. Very easy, very simple to get free money on there for your test purposes. So go ahead and do that. Then the next question here is write a program with a function that returns hello world. Use a compiler version larger than 0.5.1. So there are tons of new versions of Remix, and I can I actually not too familiar with all the differences. So they introduce new functionalities, but nothing really sticked out. So we remained at this these older versions, and yeah, we can try this Hello World example here and adopt a little bit what's really going on here. So maybe let's do it like this. Very good. So we take this smart contract, just remove the non-interesting parts or not relevant parts for right now. And we now only have to define a function which returns hello world. So we have a function called hello world, and it has no inputs. We define a public, we define returns, and we define string as a return. And what is he complaining here? Yeah, we need to set memory here. Or it's the other way around. I'm confusing it all the time. So also when we talk about exam here, if I expect you to write code, these are details. I won't subtract any points. So if you're missing some of the semicolon, then we can talk about that. But the order of parameters or stuff like that, that's not really important. And then we can say return hello world. And we could say, okay, this function state mutability can be restricted to pure. We can do that right now because this function does neither read nor write to the state of the smart contract. And now we can deploy this one. And as you see here, it returns hello world. So very simple example here. Let's see about that. Question about what was the point of that memory in the function return. So this string memory is a very good question. If you provide parameters to the function, or if you have parameters that are that you're returning values, then you need to declare if they are either in the memory or in the storage of the contract. And this is a change they introduced in 0.5.0 due to some kind of inconsistencies and security issues, but I don't really recall the details here. So that's something we just do. I'll look it up what exactly was the reason for that. Why? Next question, is the constructor for the hello world smart contract necessary? So if the constructor is empty, then you do not really have to or you do not have to provide a compiler, a constructor. If it's there, it's fine. If not, it's also fine. But in general, what they recommend in terms of best practices is that you are able to provide one, because then we know that it's there and it's empty. So more like best practice, but not really necessarily required. Okay, let's go back to we wrote this smart contract, and now we have something like a question: install the Solidity compiler and compile your program, turn optimization on. Also general the application binary interface. What is the ABI used for? So if you want to install this, there is an explanation in the solution slide. I won't go through that. I think that's only if you're really interested in command line stuff, but it's not really interesting for us right now. I would recommend to do it everything in Remix. If you try it yourself, then you don't have to install software. That's the most easiest part. And I know some Solidity developers which really did a lot of work in this area, and they even said, okay, only when we deploy smart contracts and when we really deploy our productive systems, we usually work with Remix, because it is very reliable and works very well. So seems to be a good choice. Obviously, if we do a lot of testing, if we do a lot of integration tests, for example, then you rely on other tools like Truffle or Ganache. These are software, we will introduce them, but it's not really important for us, because this is really a software development question. Okay, but I can show you anything, the optimization, I can talk to you about that, and about the ABI. So when we look at our browser again, then we see that we have when we compile the smart contract, then we can see something like enable optimization. So the smart contract can be optimized in two ways. First of all, it could be optimized for the execution. So when a lot of people execute the smart contracts, for this cost to be as low as possible, or it can also be optimized for deployment, so that when you deploy the smart contract, that it's as cheap as possible. And we can switch this on and off. What I'm missing here is a parameter, the runs parameter. So you can, when you optimize, you can put an additional parameter in terms of, okay, how many times is a smart contract executed, or how many times are you expecting this smart contract to be executed. And with this information, the smart contract, the optimizer basically optimizes either for deployment or for execution. And that's something you see, for example, here. If you look at the verified contracts on Etherscan, let's just take this one, look at the code, and then you have a optimization enabled no with 200 runs. And this 200 is always the standard value for this optimizer. And you see optimization enabled here, for example, and then you see, okay, yes, with 200 runs. And quite an interesting discussion with this optimizer. Also, a bachelor thesis is currently running at our chair to investigate a little bit about this this optimizer here. Okay, let's continue here. We want to talk about the ABI. The ABI is here, so you can take a look at the compilation details. So this will give you everything to know about this smart contract. And you see the bytecode, for example. You see Web3 deploy, function hashes, guess estimates, stuff like that. Runtime bytecode, a lot of stuff. And I think there should somewhere I saw that. Yeah, there the ABI. And the ABI is the application binary interface. So what is it and what is it used for? The ABI basically describes, similar to an API, an application programming interface, how you can access functions from the smart contract or of the smart contract, and what parameters are required and what parameters are returned, so to say. And if you look here, we have this function 0, or the first function here in this ABI. And for example, it says constant is true. There are no inputs required. The name is hello world. There is one output in types of string. It's not payable. It's a pure function and it's a type function. So the case here is that you're able to easily understand what the smart contract does and how the smart contract works without having to read through the source code. So that's the idea here. And we can take this ABI and copy it and use it in other applications. So for example, if you have some kind of we do a lot of Node.js development, and you could easily paste this into a Node.js, into your Node.js server source code and say, okay, please execute function XYZ and do some stuff with that. And with this ABI, the server exactly knows what to do with this information. And I want to give you in the next question here, if you look at Foxit, we will postpone this because we want to go to that one. Because we first want to deploy the program on Robson testnet and issue a transaction to call your function. And then we take a look at on Etherscan. And where can you find the output of your function? So that's something we want to do right now. I'll have to do it like this. And now we want to take this this very super awesome program we written to deploy on the Robson testnet. So what we do here is we go to deploy and run transactions, and we have to go up here and select injected Web3. So what is injected Web3? Web3 is the technology that allows your browser to access a full node and basically to issue transactions, connect to the network, and get information about the network, smart contract, stuff like that. And here we have Robson 3 network, because in my MetaMask, I am connected to Robson network here. And you see my account, but that's not real money, unfortunately. And now we are able to say, okay, taking this account here, that's the only one left, that's with my 3.9 Ether. And we take this untitled one Solidity code and deploy it. What happens here is a MetaMask window shows up. I hope you see that. Last time you didn't, I think you do now. You see here, okay, account 1, that's my account, to Neuer smart contract. So that's unfortunately German. And a new smart contract, so smart contract execution, and we have our gas fee. And so we see that's the data we deploy on the smart contract. And we could also change some of the gas costs here, but that's not too important here. So we have 1 GUA, what we define here. And that's our total cost here. And now we confirm it. And what happens down here is that it was sent to the network. And now we see it's pending, so it's not mined yet. Into a block, so we need to wait for a second, and then we see our smart contract deployed. And while we do that, we think about the next step in our exercise here. So we deployed our program, and now we want to issue a transaction to call our function. And we need to set, we need to do a little bit about that. I'll show you in a second. What we do here is we use My Ether Wallet. My Ether Wallet is another software which allows you to access your contracts, access your do it like this. Sorry, access all the details about that, and it looks like that. And this is something like an online interface for the regular user. It's not for the developer. So Remix is for the developer, but this is for the regular user if you participate in ICOs or something else. And now you can put access to your wallet and say this MuseX, so MetaMask. And then you can say, okay, I'm accepting the terms here and I want to accept MetaMask. So what also has happened here is it would usually ask me if I allow the access here, but I already did that today, so it doesn't ask me again. And what we see here is we see our balance, we see our address, we see our network, and what we can do here is we can interact with the contract. And this is what is the interesting part here. We can take this. We now have this address here. So this is the smart contract on the blockchain. The transaction went through. So that's our smart contract here on this address with the bytecode we deployed. And now we want to be able to interact with the smart contract here. So what we do here is we copy the contract address in there. And what we also need is this ABI. So we go here, go to the ABI. This is copied to a clipboard here, and we can paste it here. The interesting part here is we have a pure function. So again, we do not neither read or write to the state. So the execution is very simple. So if we press continue here and say hello world, the result will be hello world. So it executes it instantaneously because it knows it does not write to the state. So that's a little bit unfortunate because we want to write this transaction nonetheless to the state despite it being pure. So let's go again. Let's clear everything and let's try that again. So take again this ABI. We need to adopt it a little bit. We want to have this address here. Let's take this one, enter it here. And now we have to manipulate two things. So we have to first of all remove this constant from true to false. And we need to remove this one. The state mutability pure is saying the software, okay, you do not have to send the transaction, but you remove that. And then you can say, okay, continue. Select the function hello world here, and then we can actually create the transaction. Why did I do this, or why is it not able to do this directly within this interface? Because it's not needed. So this is a software for the end user, and it should protect the end user. And what we are doing here is basically we are just doing this for fun here, and the user should not pay for functions to execute if they don't have to. And now we need to write, and our MetaMask pops up again here, telling us, okay, you want to execute a smart contract, go ahead. And we just want to do that. And my Ether wallet tells me, okay, that's fine. And what we see here now is, if we refresh this, then we have this pending transaction. So we issued a transaction to call your function. And in order for your wallet to actually send the transaction, you might need to set the constant field of the function in the ABI to false. So, and you also need to remove this state mutability pure. Do a transaction on Etherscan, where can you find the output of your function? So let's check until this transaction is mined. So what happens here is sometimes on Etherscan that is removed the second it's mined into a block, and then you just need to reload the page and it shows up. And this is our super awesome transaction. What you see here is you see this one. This is the called, and this is the function identifier. So the function basically identifier is a very short way to uniquely identify a function, and you put it in there, and Etherscan is so nice and tells you exactly which function this is, and that it has no parameters here. So what is now the result of our, oh, you did not see that, that's unfortunate, I'm sorry. Let's do it like this. So this is what is provided here as text. And this is the function hash, the 4-byte identifier of the function hash, of the function. And Etherscan tells us hello world. And now we want to understand where is our output. And if we want to do that, we need to go to a parity trace. So because this return value is not used anywhere, so it's just thrown into, it's returned to, there is no recipient of this value, because there is no concept of getting the answer to that call. And what you have to do is you have to go to the parity trace here. And this parity trace would allow you to see, okay, what is the input? That was our function, and this is the output of this function. And if you click here and say, I want to see the text, then you see exactly what you need to see is the hello world we wrote in the first example. Okay, so one question here, how would you usually distribute your contracts ABI to the users in the real world? So usually this ABI is used on websites. So you would go to a website, and this website has information already about the contract. It knows where it is, it knows the ABI, and just says to the Web3, to MetaMask, hey, if you click that button, you will issue a transaction, or you issue a transaction to the smart contract with these parameters. And MetaMask says, okay, that's the transaction. Will you please confirm or reject? And that's something that's how you would do this, usually with Web 2.0 or any other means. So usually this ABI is nothing you would send to a user, but it's more like you provide it with your regular web application. Another question, is the cost of this transaction same as calling the function from Remix interface? Let's assume function actually sets a data. That's I think it should be the same. The function from Remix interface should cost the same, but as Remix does not allow me to manipulate the ABI in that way that my Ether wallet allows it, we cannot really test it in that case. That's what's going on here. Okay. Let's get back to the exercise. What is the difference between bin and bin runtime compiler options? Which should you use to deploy your contract? So the bin and bin runtime are just two compiler arguments you can use, and basically they allow you to output two different versions of the bytecode for deployment on the chain. And so people think that if you send a smart contract to address 0 or to address null, then this data gets deployed on the blockchain. But that's usually not the case. But this code is executed. So if you send a transaction to 0, then this code you provide gets executed. So you do not only provide the smart contract you want to store on the chain, but you provide a program that returns the smart contract bytecode that you want to store on the chain. That's the part here. And the bin actually outputs the complete package in terms of bytecode plus the bytecode that stores the smart contract, or this bin runtime, which only outputs the runtime bytecode. This can be used for debugging purposes, for security penetration testing, something like that, but also not too relevant for us. You should use to deploy your contract the bin one. That's very important. We did this G already. Okay. Half an hour left on the clock. Question number 4. In the lecture, you were warned that using address.call is dangerous. In this exercise, we will see one reason why. Consider the following vulnerable smart contract. This is the smart contract here. We will talk about it in a second. Describe the basic functionality of this contract. So let's take a look together here. We have Pragma Solidity 0.4.24, so one of the most popular compiler versions actually. Contract is called Dangerous, starts in line 3, ends in line 18, and in line 5 we have a mapping. And this is a mapping is a storage field which allows you to like a table from address to an unsigned integer. and is called deposits. So it's neither public nor private. So it's if it's not public, it's internal. And deposits. So we have a variable there. We have a function called deposit money, which is public and payable, so everyone can execute it, and you can send Ether to it. And it's very easy because it just takes the message value, so the value of the message, so the value of the transaction, so the money you send along your transaction, and plus equals means it adds and stores to this variable. So it looks into this table and says, okay, where is the msg.sender, and adds the value to that. So it's basically a wallet contract. I can send money to it, and it deposits the money for me. And the second function allows me to withdraw money, and I'm telling it how much I want to withdraw. So uint amount is in this term what I wanna withdraw from there. And it's also public. It's not payable because I don't want to send money to this function. And the requirement here is that deposits of the msg.sender, so your deposits that you previously have deposited with this function, is larger or equal to the amount you are providing here. And if msg.sender.call.value amount, then it reverts. So that means if this function somehow fails, then it reverts, and so that it rolls everything back, and then it subtracts the amount it sent to you from your deposit. So if you withdraw everything, then definitely all the money is gone from your account to your, from the deposit in this smart contract to yours. And that's what's really going on here. That's the important part here. So let's take a look at the second question. What exactly happens in line 13? And that's something that's, so to say, the key here. And let's take a look at that in detail here. So let's get back to line 13 and look at it in detail. So first of all, we have let's assume a little bit this part here. So we have a call.value in terms of amount and in terms of an empty bracket. So what happens here is we use msg.sender, that's the address, that's the recipient of this call, and send a message to it with, first of all, the value, the previously defined amount, so the money, with an empty bracket, which says we have no arguments. We don't want to execute a function. We just want to send to the callback function there, and there is no .gas. So you could do something like a if we would do something like a let's do it like there. Make this a little bit smaller. So if you do something like that, you can also specify some gas you wanna give to this other contract. But as this is not defined here, we forward all gas we have to this smart contract, to the other smart contract. So that's not there, unfortunately. And to remove that one. And if this fails here, so that's the exclamation mark, it somehow fails. It doesn't return true, but false. Then we revert the state, the transaction, so everything fails. That's the important part here. And this is the vulnerable part here. And if we go to question C, this is the so-called re-entrancy attack. So the contract is vulnerable to a so-called re-entrancy attack. Describe the problem. The problem here is that we handle the execution to this external smart contract, and this external smart contract can do whatever it wants with this execution. And the problem here is that this called contract here could use its execution to call back to this smart contract and withdraw again money. So it could this function, this line 13, executes another smart contract that executes line 11 again, and so on and so forth, collecting money until the account is empty. So for example, if you look here, we can do a little bit of visualization on the screen here. So we have that's the regular smart contract, and we have an evil smart contract. And this evil smart contract basically calls this withdraw. And what this one does is says, okay, here are your, I don't know, 1 Ether. And with this environment, it calls again, gets back, again, get back. And every time it returns, it gets 1 Ether, although it initially only paid 1 Ether. So that's the important part here. And we see why in a second, or how that works in detail. And but that's the re-entrancy attack. And so assume the contract holds some funds. Write a smart contract that exploits the vulnerability and transfers all Ether from the contract to your own account. And that's a very interesting task. I would ask you to do this on your own. I will not write it line by line with you, but I will go through the solution line by line so that you understand what's going on, and then we will execute it on Remix, and then you see that it actually works. So let's take a look at our Chrome window here. I'll make this a little bit smaller, and let's take a look here. So we have our vulnerable smart contract here. Let's remove everything we have here. We go to back to our JavaScript virtual machine. I think we need to reload so that it does not get confused. We have our vulnerable smart contract, and we have our JavaScript virtual machine, and this is our vulnerable smart contract. So I just copied from the exercise, and we take that one and deploy it with our regular account. So it's dangerous, and we can let's make a little addition to that. Let's make a function balance. It's public. It returns an uint memory. No, it does not uint. So we leave memory out here because it's the older compiler version. Sorry for all the confusion here. And what we just return is returns this dot balance. I don't know what's the So I think I might have I'll have to check how this one works. So I'll just copy this one here. Why doesn't Okay, so this one works here, and this one allows us to display displays the contract balance. So currently it's 0. Now we can take this one and say, okay, we want to deploy, let's say, an Ether, and put it in the deposit money. So transaction worked, and you see it's stored in that. This is a very large number because of this conversion from Ether to Wei. So because Wei is the smallest unit there. And now we want to be able to exploit this smart contract. And how we do that is by using another smart contract. And let's take a look at that. So we create a new file here, exploit, and this is the contract here. First of all, we need an abstract interface of our vulnerable smart contract, because we want to be able to access these functions. We do not need to implement them. We not just need to be able to know the interface, so to say. And then we have our contract exploit. What we do here is we first start with let's zoom a little bit. We start with a line dangerous D. This is, so to say, the contract dangerous. We reference with a variable D. And we have a uint public deposited. So this is a variable we need later on for knowing how much money we deposited there. And then we have a constructor, and this constructor is basically an address to the to be exploited smart contract here. And we have a function attack, and this function attack basically is public and payable. So me as an attacker need to pay my attacking smart contract to have some money, so otherwise it won't be able to withdraw funds. And what it says, okay, require msg.value larger than 0, because it needs some money to withdraw other money, so obviously. And what it does now is it says, okay, it deposits the complete money that it received from me into this money, into the smart contract, into this exploitable smart contract. It stores what money was deposited, and now it withdraws this deposited money from this vulnerable smart contract. And you might ask now, okay, and sends the money to the MSG sender back. And this is something that's very interesting here, or not interesting, but not too interesting, but it automatically also sends the money back to my externally owned account. So for example, if you look back here at the iPad, so obviously when we remove all this right now here, again, the same situation. So we also have a smart contract, and we have an externally owned account. So that's us. We say attack. It does all this execution, returning all the money, and at the last step, it also transfers the complete amount, the 10 Ether, back to my externally owned account. If we remove this line, we actually see the money that was stolen, but it's both ways seeable as on our balance sheet and so on. Okay, so let's get back to Chrome here. And we have the interesting part also is here, this function payable, public payable. And this is our, as you see, it has no name here because it's the fallback function here. And you see, if address d.balance is larger or equal than deposited, then we say d withdraw deposited. What does this check for? It checks if this contract which is under attack has enough funds left that we can deposit from. So if you would continue to withdraw from the smart contract, you would, even if it has no balance anymore, this complete transaction would fail and all money would be back at the original smart contract. So you need to have some kind of a execution, so a break execution, a check to see if you got all the money. So let's try this. So we have this smart contract here with 10 Ether and all on the first account. We switch to the second account. The second account deploys this smart contract here, so we not this dangerous, but we want this exploit. So because we cannot create this one, but we can create this one. And now we say we want to deploy this, and we need to provide an address of the smart contract here. So that one with 10 Ether. So we take that one. So this is always copied to clipboard and deploy it here. And now we have this exploit smart contract here. And what we see here is we have a contract balances and we have deposits, both are empty right now. And now we go here and we do not want to pay 10 Ether, but we just want to pay 1 Ether. That didn't work. So we want to pay 1 Ether. And now we press the magic button attack. And what happens here is working. And it worked. And as you see, the account received 110 Ether. So the 10 Ether that we were deployed from contract 1, from address 1, are now in the hands of the second address, the attacker. So that is what happened, and this is how it actually worked. So as you can expect, this one was quite expensive. So let's take a look here. So we have this transaction cost here, 252,000 gas. But as you can imagine, this is peanuts in comparison to what has been stolen on Ethereum, and therefore this attack remains dangerous. And to conclude with that, that's the attack from this from the DAO. The original DAO was vulnerable to this attack, and that's what really made the network split, so into Ethereum and into Ethereum Classic. Okay, so let's take a look at the exercise here. We did the D and question D, and how could this attack be prevented? Let's take a look again at the Chrome window here. So how could we prevent this attack from happening to this vulnerable smart contract? So first of all, I mentioned the first thing here is this: if you do not provide this call is always a bad idea if you do not want to execute the other smart contract but just want to transfer money. There are better functions for that. But also one simple change would have made this possible if you just move this line from up there to here, from down there up there before. So first withdraw all the money from your internal system or from your internal variable, and then send the amount. And with that, you would not be able to re-entry again this transaction, this function. And the important part also here is there is no worry that you withdraw. So for example, if this would fail, then the money would still be there, because this revert transaction is always saying either everything works correctly or we put everything back where it was. So reverts the complete state. So there is no danger in a person not receiving their money, or a person reducing the deposit but not receiving the money. So that's the part here. Okay, I think that's it for this exercise sheet.